The problem states that we have a row sum and a column sum respectively. Row sum is an array, column sum is an array. The row sum array has the individual summations of all the row elements in that particular row. Suppose this was the row, so y1 is my summation. Similarly, 3 plus 0 is 3, 1 plus 7 is 8, which is the row sum. 3 plus 1 is 4 and 0 plus 7 is 7, which is the column sum array. Now the problem over here is they have not given us the output. They have just given us row sums and we need to calculate what the output is. Output is the original array that can form such row sums and the column sums. Now it has been given that there is at least one. Now to prove that at least one, this is the condition that they have given. At least one solution will be there. Now if this was not there, then there might have been a problem, but this is always the case, right? Sum of column sum equal to sum of row sum. We'll come to this later. This is a very important point. So this was the problem brief, right? Now coming to what were the constraints, that there are no negatives. This is also a very important point to remember, that there are no negatives. Now what all came to my mind before I was going towards the greedy solution was, the first thing that came into mind was maybe equations might work, because this is at the end a mathematical equation. x1 plus x2 plus x3 is y1, which is given to us. We need to find out x1, x2 and x3. So suppose now we'll have like m into n variables, right, over here in this array of x's, and then we will have y's which are only m plus n. So now we have only m plus n equations to solve for m into n variables. So that cannot be done, like it cannot be done unless and until we predict some values and hit a trial and error method. Only we'll certainly know what the values of x's are if there were m into n equations for m into n variables. The number of variables, unknown variables, should be equal to the number of equations that we have, relations. So this was not the case. So this thing cannot be there. So equations wise we cannot go. The second thing which came into mind was backtracking. Can backtracking solve this? Now coming to backtracking, if I say that can I backtrack, in the sense I will choose all the 10 to the power 8 elements. If you see, there are 10 to the power 8 possibilities that one element can have. Can I choose 10 to the power 8 possibilities? I can. I will go to each of the cell and I'll put from 0 to 10 to the power 8 values, and then I will for each value check for another 10 to the power 8 values of the other element in that array, 2D array. Now again for 10 to the power 8 values of this, again I'll check for 10 to the power 8 values of the other one. So this is 10 to the power 8, 10 to the power 8 gets multiplied and becomes exponential to 10 to the power 8 to the power of 10 to the power 5, which is very, very large and computationally not possible over here. So we have this backtracking solution also negated out from our. So now if the conditions, if we see something, we can say that we will have to choose at a certain point in time, we will have to choose some number, because we do not have equations to solve it, and for a fact we do not know what that particular value is. It can be 5, it can be 3 also, because there are multiple number of possibilities. So now, and we cannot try all the possibilities because that is out of the question, because backtracking is not possible. We cannot have random selection. Now the best way is to have a best selection. Best selection comes in when we optimize for local optimums and get the global optimum. So now if we see for a local optimum, that then we get the greedy solution in mind, and now we have that greedy solution. Greedily we'll be choosing some number, right, for each of the cell. Now when we are choosing some number for the cell, how can it be the best possible scenario that we'll be choosing that cell value? So best possible scenario, we can take this example. Suppose I have a number line, right, from minus infinity to infinity. I have a number line, I can choose any value. Now in the question it is given that it cannot be a negative, so all these values are out of question. Now suppose I say there are only 3 cases possible over here, that the row sum at any ij, this is a ij wala column, ij wala cell, sorry. Now at any ij cell, the row sum of I and the column sum of j will have some values. Now those values can be different, which is this case. Either of them can be greater than each other, or else both can be same, that is the other case. These are mutually exhaustive cases. Now if we say that suppose minimum of these two, which is x, right? Let us take x for sanity purposes, simplicity, x. Let us say that x was the minimum out of these two, and if we are taking anything greater than x, I am taking a value which was greater than x for this cell. So I suppose take y, and y was greater than x, so I know that the row sum of it was x only, and the cell value itself is y, but the whole row sum is only x. So now y minus x is the difference that will have to be somewhere, right? Y minus x is my value, suppose z, so minus z should be there somewhere, so that y plus of minus z becomes my x, right? So this is a negative value. Now what we have hit a roadblock, that contradiction, that it is a negative value, and in the question we have that we cannot have negative values. So all these values are out of contention now. The minimum of the column sum and row sum, say greater values, are out of contention. Now we have only 0 to minimum of row comma column sums values for that index, right? We have only these. Now in this also we need to select the best, greedily best possible way. The best possible way to select would be, suppose I will choose that, okay, let us say that I won't choose the minimum of these, I will choose anything other than minimum, So for simplicity I took only one case, right, to contradict this. I have taken that only 0 0 0 0, this is a case, right, where I can take all the zeros, and then at last I can fill it by saying minimum, or else minimum minus 1, say, because we cannot take minimum, right? So say minimum minus 1, and then 1 I put over here, and everything else is 0 because it had to be all positive, right? Now can I have that this minimum minus 1 is already greater than the column sum? Can there be a possibility? If there is a possibility, such possibility, then we are contradicting the fact that we'll be giving a valid possible answer in all scenarios is possible when we are taking less than minimum values. So this is contradicted now. Now we'll have that, okay, we cannot always have a solution if we choose only less than minimum. So can we prove that if we take minimum we are guaranteed to have a solution in these cases? Can we prove that? So this is the only proof that we need. So do we have an answer which is a possibility for minimum at each step? If we are considering minimum at each step, do we have a possibility to prove it? So for that we can use this. Initially we know that the sum of row column and the row sum and the column sum are same, which is equal to the sum of all the individual elements, m cross n elements in the array. We know this. Now at each step what I am doing, I am removing x1 and x1, suppose, from the sum, right? From the sum of each of the sums. From both of them we are removing x1 and x1. Now this x1, right, x1 plus x2 plus x3 plus xmn, we know that from a fact that if we are taking only minuses, if we are taking only the minimums and we are subtracting it, then we are at each step, suppose the total sum was total sum was 80, we'll be removing some value from this only. So 3 will be removed at first step, suppose. Next step, we will be removing some 1 only, and then till the last step we will be removing only till 80. So we cannot exceed 80. So somehow to exceed 80, which is like the contradiction to this, in the sense कि we'll have to exceed 80 to bring to the fact that we cannot form an answer. So suppose after m plus n minus 1 steps, right? This is the case where m plus n minus 1 steps have taken place. Now after these number of steps, initial sum, the current sums are these, which are initial sums minus the x1 plus x2 plus x3 plus xn, right? Now we know that these two values are already same, and we know that these two values are 100% same. So now these two values are also same. Now for the last element, we know that we can just put in whatever value this was there in either of these two, because it will always be same. Now what was the role of like minimum per se over here? Minimum only made us sure that the total x1 plus x2 plus xn, this should not exceed 80. It should be equal to 80 only, always. This is making sure. Suppose it was not equal to 80, what I will have after all my steps are done, I will have that this is not equal to 80, this won't be equal to 80 after n number of steps, this whole thing, and this won't be equal to 80, right? So some amount of this will be left, what we'll call some amount of out of 80, some amount x amount will be left out from the sum, which we cannot have, right? Because we know the total sum of all the elements in that array has to be 80. But we are saying that right now the total sum of all the elements in the array is not 80, but it is 80 minus x. So if we are ensuring that it is 80, if we are just ensuring that it is 80, that is the main crux of the problem, that we are ensuring that we will have an answer for sure. So if 80 is there, then we are equally distributing that 80 total sum, right? This total sum, this total sum, we are distributing it properly in those m cross n matrices. We are not exceeding this sum of 80, we are not going lesser than this sum of 80, right? So if we are taking the minimum, so if we are taking minimum, we have proved that we will definitely have an answer if we are taking the minimum, because we are not crossing the 80 limit, and it will never be less than 80 also. It will always be equal to 80 only. So we'll be covering all the cases where the elements, it can be 0 also. Many of these will be 0 also, because whenever we move from one row to the other or else one column to the other, we are effectively deleting that from contention now. In the sense, we won't be processing that. From the processing of that row is completely done now. That is the whole point. So this is very close to like maybe the proof by contradiction thing, where I tried to get to the best possible value, which is the local optima, to get global optima value. So this is the basic crux of greedy, right? This is what greedy is. So yeah, if we go through the solution, right, we just initialize an array with m cross n array, which will be our answer array. Initialize everything with 0. At each step, I will choose the minimum, I will put it there, and then I will go on. If this minimum was from the row, then I know that in this row I cannot put anything, I'll just do I++. If this was from the column, then I know that in this column I cannot do anything, I have to keep zeros only, because negative is not possible. Negative is not possible. This is the main point. So I'll have to do j plus plus in that scenario. So this is like we have to take m plus n steps to reach the final from 0, 0 to m into n part. I mean m minus 1, n minus 1 wala matrix from 0, 0 if we are taking zero based indexing. So we'll be filling everything, and whatever is not filled is already 0, which we don't need to care about. It is already done. So at each step what I'm doing, I'm incrementing either I or j at each step. This is a step, this while loop, and we have m plus n steps. In each step I'm just taking the minimum, I'm subtracting it from both row and some columns, and then this either of these two will become 0. Either of these two will become 0, that is for sure. So this same thing which I have written in this way if else condition can be written like this also, that if row sum is equal to 0, we know that in that row nothing can be done, so I'll just do an I plus plus. And if this is not the case, then the only case possible is that my column sum is equal to 0, which is handled by this j plus plus. So yeah, that is the whole solution. Hope you liked my future self likes this. I'm also learning, in the sense I tried to do things, it might not be perfect, but this is how I understood the problem. So yeah, that's it, I guess.